Morning. Mm-hmm. Good morning. How are you? Good. How are you? Good. Hey, Jason. Hello? Yeah, I can hear you. I'm just about to start class in like 30 seconds. So,
Okay, so go ahead. I'll send an email or we can talk after.
sounds good.
Okay.
Thanks. Bye. Okay. All right, let's see. Let's get my stuff up here. See where we left off. Summary, that sounds like where we finished yesterday, which is a good place to start today. All right, so I emailed you this morning and said I'm putting out a last call for homework today because I'd like to post the solutions to the chapter 13 and 14 homework. Chapter 17, which has been posted, which we're now in the middle of, that's going to be due our next exam, third midterm exam, if you like, or during the term exam, is next Wednesday. So I have it due on Wednesday. For obvious reasons, there's not going to be any extensions on that one. You really want it finished before the exam. And I think the exam will focus on, at least in terms of the calculation stuff and the homework we've been doing, since the last exam, it's been mostly chapter 13, 14, and now 17. So those 3 sets of homework problems are going to be the bulk of the stuff that you'll see on the next exam. I'm also thinking that we will do another round of your paradox presentations. Maybe some of you only need 1 more iteration, but I think I'm going to put everyone through 2 more iterations. So I'm thinking in class on Monday. That means this weekend is the time to really get going with the changes that we talked about. So if you have any questions about which way to go or how to graphically describe something, certainly talk to me after class today or after class tomorrow, or send an email or something and we can try to fill in more details. I've talked to some of the groups in greater detail than others, and some people had a really good outline. It was just fine details that maybe could make the talk better, even though the basic thrust was pretty good. Any other housekeeping issues before we pick up where we left off in chapter 17? I guess we can sort of see the end of the semester now. Chapter 17, I think, should be finished by tomorrow so by the end of this week. There are just a couple other topics, and nominally part of it goes with chapter 18, and it's the idea of E equals mc squared, or the relationship between energy and mass. And there's a couple other ideas, and that chapter, if I remember correctly, is a pretty difficult read. Many of you commented that chapter 17 was a difficult read. Well, chapter 18 just introduces a lot more concepts from physics, and if you're someone who hasn't had physics before, it can be kind of a rough go to think about what momentum means and what energy means and that kind of stuff. Those concepts are introduced and used in that chapter. So I'm not sure if I'm going to make that reading optional, but in any case, I will present everything in class that I really want you to know. I don't think I have any homework problems on it, but we'll practice some things on worksheets in class. And I can let you know that will probably be the only thing that you haven't seen on the midterm exams that might appear on the final. So we'll practice some problems having to do with nuclear decay and seeing how E equals mc squared makes itself known experimentally and practically in the physical world. Okay. As always, I've got to check to see if my clicker is working and dim the lights in the room, so hold on just a second. Okay. So this is a summary of what we did yesterday, which was quite a bit. You know, we had the idea of space-time diagrams before, but without the axes. The axes properties encode all of the things that we've learned about relativity so far. And you saw in the reading for chapter 17 exactly how to extract those out. Now, they may not have stuck, but we're going to talk about them today in more of a visual, animated way. I know Merman was fairly visual, but this will be probably even more visual, and I can sort of animate things through. Hopefully it clarifies. Okay, so the idea, well, some of the things we talked about last time was that we were going to plot x versus t, but just in order to make sure that the axes had the same units. So here I'm labeling them in light seconds and light seconds. We could also have them in meters and meters, right? If t were in seconds and c were in meters per second, then this would have units of meters, and then I could label x in units of meters. But the important thing is that they're labeled the same way. And we agreed by convention, it's just sort of simpler to have the spacing between 0 and 1 on the x-axis be the same as the spacing between 0 and 1 on the t-axis. Because a light beam goes exactly 1 light second in 1 second. So that means a light beam is going to travel along a 45-degree line, and that's true. This one happens to be emitted at the origin, or it passes through the origin, so it was at x equals 0 at t equals 0. But a light beam emitted at x equals 2 at time t equals 0. You know, if it were shown to the right, it would move in this direction. If it were shot to the left, it would move in that direction. And I shouldn't say a beam, I should say a pulse. We're thinking of a very short pulse, like a flash of light. And we're living in a one-dimensional world, at least for right now. So there's only in the positive x direction and the negative x direction. We found out that, you know, for other reference frames, the time axis, of course, is going to be tilted with respect to the time axis in the original frame. I mean, in some sense, we sort of arbitrarily decided. There's nothing special about this frame. You might think, well, why is this frame lucky enough to get those perpendicular axes and all the other frames have the, you know, kind of not so familiar axes that are tilted at weird angles with respect to each other? And the answer is it's just completely arbitrary. You know, somebody has some frame and somebody's lucky enough to get those perpendicular axes, and then that makes all the other ones not perpendicular. So one manifestation of that is that the time axis, of course, this has nothing to do with relativity, but even Newton, we talked about, would say, well, you know, if there's an object moving, its world line looks like this. If we want it to be at rest in that frame, the time axis better tilt exactly along with it. Okay, so in this case, it says, I know it's hard to see, at least here in the classroom, because the screen's a little washed out, but this is corresponding to V over C equals 0.5. And we learned how to calculate exactly what angle we should tilt that with respect to the vertical at. We found out that we just set tangent of theta equal to V over C, and then that means that theta is the inverse tangent of V over C. And if your calculator is in degree mode, you'll get an angle in degrees, and we measured that with protractors yesterday in class. Okay, so we found out how to tilt this angle, and then there was an argument that this had to be tilted as well. The x prime axis, corresponding, you know, to a frame which moves with respect to the original one, has to be tilted up if this frame is moving to the right with respect to the first one. When I say to the right, I mean in the positive x direction. Then this has to be tilted up. And that came from the relativity of simultaneity. And you can also see that if we label, you know, if we put equal distance tick marks on these axes, then we succeed in having the speed of light be exactly the same in all frames. So the principle of the constancy of the speed of light, in other words, if, oops, have I lost control? Here we go. In the original blue frame, light travels 1 light second in 1 second, right? And in this new frame, if I go up 1 second, light has gone over 1 light second. And we're always moving parallel to the x prime axis and parallel to the ct prime axis when we're trying to find coordinates on there. All right, oops, I skipped over something. Okay, so that we decided we're going to space these equally, but the question is, what's the spacing? And the answer through, a not too difficult argument, so just a little bit of geometry, was that we got this scale factor, and that scale factor means whatever distance on my paper, maybe measured in centimeters, I have between the 0 and 1 tick on the original axis, this distance, as measured on the paper, between the 0 and 1 ticks on the x prime axis and the t prime axis, since we're making those distances equal, is going to be the scale factor. Whatever this number is, it's a number bigger than 1, times this distance. So if this is 2 centimeters between 0 and 1, this would be 2 centimeters times the scale factor, which is that square root. It's just determined by v. Okay, so here's another frame moving with respect to the first one at an even faster speed going in the plus x direction, different angle, different tick mark spacings on there. Notice the more they tilt inward, the faster the second frame we're considering, say the green one, is moving with respect to the blue one. The more extreme the spacing disparity gets between this distance between 0 and 1 and this distance between 0 and 1. So as they squeeze together at a smaller and smaller angle, the distance between tick marks gets bigger too. That's all baked into that scale factor formula. Here's another example of a frame that happens with respect to the blue IRF. This one's moving to the left at a certain speed, minus 0.5 meters per second. In other words, it's moving in the minus x direction. So the x and t axes are tilted in the opposite direction. Questions on that review stuff? That's kind of what we talked about yesterday, the nuts and bolts. It's easy to forget why you're doing these kinds of things, but the idea was we considered the length contraction, we considered the relativity of simultaneity and those kinds of things, so they're baked into this description of how we're thinking about the axes. Now, the important thing about this is that it's easy to get sort of befuddled by all these different axes that we're considering here, but one thing we're going to keep in mind is that underneath all of these axes, there's the same collection of events. Remember, an event just means some particular location in space at some particular time. Maybe a firecracker went off there, maybe nothing happened of interest, but that's still an event. A particular location in space at a particular time. Something might have happened then, and maybe we could all see it and measure it. And underneath all of these are all saying, well, we're going to assign different x's and t values to an event, right? I might say it has a big X and a small t, and you might say it has a small x and a big T. But the idea is underneath all of those axes, those are just different biased points of views of observers. There's a collection of all the events. Each one of these points in this plane is an event. And everyone agrees on the collection of events. It's just how we assign coordinates to them. I'm going to have a different x coordinate than you are. They're going to be related by the Lorentz transformation. I have to know what your t coordinate is to do that. So we're thinking there's a space-time underneath. The different bias points of view are just different ways of measuring that we place on top of that space-time. Okay? So when we talk about space for a particular observer, right? Remember, this is space-time. So we're not looking at a picture of space here. Our space is one-dimensional. And when we say space for a particular observer, what we mean is freeze time, fixed time at, say, 0 seconds or 1 second or something like that, and take all the collection of x values, we're living in this one-dimensional world, that exist at that particular time. So here is, at one instant in time for this particular IRF here, this would be what space is at that instant in time. Remember, we're in the one-dimensional world, so it's a one-dimensional collection. At a later time, here's what space means to them, and so on. So those are 5 different examples of spaces, that what space is at different instants in time. In these other sets of, axes that correspond to different coordinates, IRFs, always, back when we were doing this, when we want to find out what space looks like, what we do is just draw a line that is parallel to the x-axis here, right? Because parallel to the x-axis means at a constant time. Now, what does at a constant time mean when we have these tilted axes corresponding to a different IRF? Well, all the points which correspond to t prime equal, or ct prime equals 1 light second. Remember, we have to always move parallel to different axes. So this means that this is the direction that I should move. I should move parallel to the x prime axes, and these are all the space-times points which exist at a particular time in this IRF. Okay, so here are 3 different times. Here's a time of 2 point something light seconds. CT equals 2 point something light seconds. Here's one that's about 0.6 light seconds. Here's one that's at a negative time. And this is what space looks like for that observer, right? This is all the x values at a particular t. We've got to draw a line that's parallel to the x prime axis. Okay, more extreme example. Those slices through space-time are different versions of space, right? Space now, and then space 2 seconds from now, and space 2 seconds from that. They're different versions of space. So how we slice through this space-time is different versions of space. Again, that other one that was going in the other direction, versions of space go in different directions like that, okay? So in space-time, there are lots of ways. We saw this stated in the Ney's philosophy text. There are lots of different ways to slice through space-time that correspond to what it means to be now for these different frames, okay? But the important thing, again, it's easy to get befuddled by all these different lines. Everybody agrees on the underlying structure of space-time. That's that gray sort of collection of points that are underneath. And if someone measures something and they get a particular x and a t, you can translate to a different IRF and find out what the x prime and the t prime is using the Lorentz transformation. So that's one of the useful things about the Lorentz transformation is it tells you directly how to go between coordinates in one frame and coordinates of the other. But underneath it all is just space-time. Now, let's start investigating our effects in here to see the length contraction, time dilation, and so on manifest in here. We already mentioned that, so I'm imagining here in this original IRF, which happens to be lucky enough to have the perpendicular CT and X axes there. In that IRF, we've got a meter stick, which is at rest. So remember, we're in a one-dimensional world. The meter stick takes up a certain range on the x-axis at a certain time. And of course, as time goes on, it creates not a world line, but people sometimes say a world sheet in that two-dimensional space-time. It's a one-dimensional object living in a one-dimensional world, but space-time is two-dimensional. When we ask what the meter stick is to various observers, we're going to get different answers. In other words, what does the meter stick look like at a particular instant in time? Corresponding to this frame, it's hard for me to tell here in the room, but that's the yellow kind of color. So that corresponds to V over C equals 0.5 relative to the blue axes. At a certain instant in time, this is what the meter stick looks like. This is the collection of all points on the meter stick at a certain instant in time. If we go to a different frame, say the one that was moving even faster, that was at 0.8 C relative to the blue axes, it's a different collection of space-time points that corresponds to the meter stick right now, or the meter stick 3 seconds from now. And similarly, here's the one that was traveling left at 0.5 C. This is what the meter stick looks like to that observer at a particular point in time. And it's a different collection of space and time points in there. And Merman makes a big deal about this, enough of a big deal that I actually quote him in here on page 185. Their disagreement is how the lines of constant time are to be put into the picture, but it's precisely the lines of constant time that determine what A or B, the different IRFs, mean by the stick. So if you're moving with respect to someone and you say, hey, I'm talking about the stick right now, they're going to, when they say the stick right now, they're not talking about the same stick. They're talking about different events in the world sheet of that meter stick. For the notion of the stick includes implicitly the assumption that the points of matter making up the stick exist at the same moment. Thus, the stick at a given moment is a slice of the world sheet with a line of constant time. Okay, and I should have reminded you in the email to bring your worksheet that we started yesterday, but we never really got to problems C and D on that worksheet. And I regret that I don't have any extras, I think, of that worksheet. But if you can find your worksheet from yesterday, if I can find mine, I'll remind you what it's asked. You're supposed to be measuring the length of a meter stick. And I'm going to hand out the protractors in class because, again, you're going to need to measure some things to actually assess the length of things. Okay, it looks like I actually do have a couple extra copies if anybody didn't bring theirs. So we're supposed to, in C, suppose that in the case of what was described up in part A, there's a rod of length 1 light second held at rest along the x direction between 1 and 2 light seconds on the x-axis. So it takes up the range between 1 and 2 light seconds on the x-axis, and it persists there, so it just stays, it turns into a world sheet, right? Because it's at rest there, it's not moving one way or the other. Draw the ruler's world sheet on your diagram and use your ruler to determine the length of the rod as measured in the moving frame F prime. Now notice the length of the rod, so here's my world sheet. It's of length 1 light second. If we switch to a different coordinate system, say the green one here, this length right there corresponds to the length of the stick at a particular period of time. Now you can't measure it using the same axes. You've got to use your new set of axes and tick marks that we used with the scale mark on there to determine roughly what it seems like the length is on the x prime axes. So we're supposed to do that in the case of A, and then in part C, and then in D, we're supposed to take the rest length, which is 1 light second, and apply the length contraction, and we should get the same answer. And so calculate what the length contracted version of that is and see if it agrees with your measurements that you're taking off the diagram that you drew in part A. So you're just going to continue drawing on what's above in part A. And while you're doing that, I'm not going to put the Zoom folks into a breakout room for this one because I don't think it'll take too terribly long, but you're welcome to ask questions and start a discussion in here. In the meantime, I'm going to try to sketch on the board what my part A looks like so we have something to draw on top of. I think I can see here. I guess you guys need your protractors if you're actually going to measure stuff. I forgot about that. Let me hand those out again because you'll need them for the next worksheet too. If you're on Zoom, you can just simply use a ruler for this because you don't really need to measure angles.
Can I ask you a quick question?
Mm-hmm.
Are we supposed to do it on this one, then start doing these ones on?
No, it's all C and D are just have to do with the diagram for part A. You could also do it in the diagram for B, but that would be a separate kind of calculation. I'm not measuring my angles up here, so I'm not sure mine's going to be super precise here, but at least we'll get the kind of idea. Scale factor was a little bit bigger than 2. Okay. So you're supposed to get an agreement between C and D. You know, of course, you're measuring things, so it won't be super precise, but it should be almost the same number. Let me just check the focus on here again. It looks like I'm missing a bit of my diagram too here. I think the focus looks pretty good. I've turned off the autofocus on our camera used for Zoom because it just seemed like it couldn't maintain the focus. And this way I just have to manually focus it. It's kind of hard to see the board. Is that better? I don't know. Either way is probably just as good. Okay. So the answers I'm getting here, well, let's just construct what's asked for in C. So again, I didn't measure these. My angle, you know, this doesn't exactly look like a 45-degree angle. I tried to eyeball it, but in any case, this angle is supposed to be 38.65 degrees. You know, certainly 38.5 is close enough for the purpose of drawing things. This angle is the same. And the scale factor was a little bit bigger than 2. So my numbers are 1, 2, 3. This is x in light seconds. And this is CT in light seconds. So this would be 1, 2, 3. And the scale factor we got was a little bit bigger than 2, right? So that means the distance here, I made that 20 centimeters on my ruler. That means from 0 to 1 here should be a little bit bigger than 40 centimeters because the scale factor was 2.13 or something like that, right? So it's stretched out in that direction. So we're supposed to draw a world sheet of a rod, which is 1 light second long and sits on the x-axis between 1 and 2 light seconds. So here's 1 light second. Here's the left end of the rod persisting through time. Here's the right end of the rod persisting through time. And here's the world sheet. We could sort of shade it in like that. If you're a four-dimensionalist, as we're talking about in philosophy, you would say this whole thing is the rod persisting through time. Okay, it's not, we're not, you know, of course, according to Einstein, there is no the rod at an instant in time because it depends on who you ask which slice of space-time points you should be looking at. So the only coherent notion is the rod's world sheet like that. All right, so we're supposed to measure the length of that rod as seen in the primed frame. And all we do is measure this distance along here. So we say on the x prime axis, that would correspond to t prime equals 0. So ct prime equals 0. At t prime equals 0, I'm trying to darken this in the best I can. This is the rod. That collection of space-time points is the rod according to the primed coordinate system at t equals 0. You know, at t equals 1, we would have to draw a similar one that would be going up like this there. And the question is, what's the length of that rod? So one way to do that is just to say, well, I could measure how many centimeters it is. Let's just do, so my distance between the tick marks here, I kind of erased my tick mark there, but let's take it at face value that 1 light second is equal to, I just made it, I know this isn't exactly right, 41 centimeters on my scale, right, measuring along here. Now, how long actually is this picture of the rod here? Well, to me, it looks like 27, okay? So we've got something that's 27 centimeters long, and I need to convert to light seconds. I want to know how long it is in light seconds, and I don't know how you learned about converting units in whatever science classes you have, but one way you can do to convert units, this is how I teach it in intro physics, is, hey, as long as I multiply by something where the numerator is the same as the denominator, I haven't changed it. Now, in this case, there's no way for centimeters to be equal to light seconds like that, but this is a conversion factor. So I could say, 1 light second is the same thing as 41 centimeters on my piece of paper. And then when I do that, the centimeters in the numerator cancels out with the centimeters in the denominator. And then I have to take out my calculator. So what the number is 27 divided by 41 is 0.6585. And again, take this with a grain of salt. I'm making a really messy diagram here. If I had a protractor, we could do it a little bit better. What did I say? 0.65. We'll just say 0.66. I don't know if the folks at home can see there. 0.66 light seconds. Okay, well, the important thing there is it's shorter, right? In its rest frame, it had a length of 1 light second. This is how long it is in its rest frame, 1 light second. In a frame, viewed from a frame in which it's moving, it has a shorter length. That's the length contraction going on there. Now, D is asking us to actually calculate the length contraction without thinking of this diagram at all. If we had something that was of length 1 light second in its proper frame, to get what we might call L prime, what do? Well, we multiply by that square root factor to length contracted. 1 minus, in this case it was 0.8, was V over C squared. 1 minus V squared over C squared. So when I calculate that, 1 times the square root of 1 minus 0.8 squared. Hey, it's exactly 0.6. So, considering how sloppy my drawing is, it looks like it's sort of in the same ballpark. 0.6 light seconds. And the more carefully your diagram, the closer you're going to get. The point is that not so much that we're going to calculate things with diagrams. If you want to calculate something and get a precise answer, you should use the formulae. That's what they're there for. But this gives us some intuition about how all people are comparing the same thing. The object is the world sheet, and different people are taking different slices through it when they're trying to figure out the length of that object. Questions or comments on that? That was one of the many things discussed in this chapter. So let's just go on here. Okay, so here's the world sheet for an object at rest. Get my fancy pointer here so I can stand in front of the screen. Okay, so whenever an object is at rest in a particular frame, that means the edges of the object are going to be parallel to the CT axis in that frame. So here is the world sheet of an object that's at rest in the blue axes, and I've made that rod blue in that case. It's not at rest in this frame because its edges are not parallel to the CT prime axis. In other words, they keep going more and more. As time goes on, they go more and more and more to the left of the CT prime axis. That means that the CT prime axis, which is moving to the right with respect to the CT axis, is actually going to see that meter stick as moving to the left, if you view it from the green frame's point of view, okay? Here's a blue stick at 2 different times, okay? Again, just remember, we're going to slice always at a particular time, and that means you take a slice through parallel to the x-axis, okay? How do we measure that length? Well, okay, we'll get to that in a second. Here's the stick at 2 different times in this other frame. Right, what am I doing? I'm going parallel to the x-axis and taking a slice through the world sheet of that object to figure out what the stick is at that particular time. Here's a different stick. This stick is actually at rest in the other frame. Notice the edges of its world sheet are parallel to the CT prime axis. So it's at rest in that frame. It's not moving as viewed from the green frame or the F prime frame. It is moving, of course, with respect to the blue frame because as time goes on, it's moving to the right, right? Its edges are not parallel to the CT axis, so it's moving in that case. Here's what that second ruler would look like at instants in time as seen by the first frame. Notice it's sort of smaller there, right? That's going to be a length contraction effect because this is a frame in which it's moving, and therefore we expect to get a smaller length. To measure those length, if you want to find how long something is, this is what we just did on a worksheet. You slice through the world sheet at a certain constant time in that frame. So there are different constant time slices through. If you want to find how long it is, you measure on that frame's axis for each one of those slices that's parallel to the x-axis. Measure the extent on the x-axis. If I want to find out how long that same blue meter stick is in the other frame, this is what we just did on the worksheet. I take a slice through that's parallel to the x prime axis and measure that distance as, using the scale that we have on the x prime axis to see how long it is. That's important that you use the correct scale there, but we've worked hard to get that. Okay, here's the green rod. If I want to find out how long it is in its own rest frame, well, I look at what's sliced through that world sheet parallel to the x prime axis and measure it on the x prime axis. So it's a 1 light second world sheet rod there. What's the length of the same rod as viewed from the original sheet where it's now moving? Well, it's going to be smaller than 1 light second. It looks like it's closer to 0.6 light seconds in that particular case. Okay, so that's a little bit about what an object means and how to see the length contraction in there. It's directly in there, but it relies on this rescaling that we've done on these axes here. What about if we look at 2 different events? So here are events. Remember, we don't even need the axes on here to specify the events, but there are 2 events on there, and we're going to look at them from 2 different points of view, the blue axes and the sort of yellow axes there. If we want to find the time interval between events in a certain reference frame, say the blue frame, the perpendicular frame, then what we do is, well, we already know what to do. If we want to find the time interval between them, what we do is find the time of the second one and the time of the first one on those set of axes. How do we get to those axes? We go parallel to the x-axis there, right? And we see where those two values are, and we take the difference between those values. You have to do the same thing in words if you're doing it in the primed axes. In other words, how do I find the difference in time between these two events as assessed by this frame, the primed frame, shown in yellow there? And the answer is, well, I go parallel to the x prime axis until I hit the t prime axis and see what coordinate I hit on there. Same thing for this one. And then I take the difference between those two coordinates. Okay? And the relationship between the T1 and the T2 and the T1 prime and the T2 prime that we're getting here is given by the Lorentz transformation. So it's not something you have to do graphically. What we're seeing here is how you graphically understand the Lorentz transformation equations. They tell us if we know x1 and t1, we should be able to get x1 prime and t1 prime. And this is what it looks like in this frame. You have to kind of project things always parallel to an axis in that frame. Okay? Similarly, if you want to find the distance between events, same idea. In the one frame, the blue frame, we just go parallel to the t-axis, or the ct axis in this case. In the other frame, we go parallel to the ct prime axis and read off the coordinates we hit on the x prime axis there and take the distance between the, or the difference between those values, and that would be the assessed distance between event 1 and event 2, as seen by that primed frame. Okay, so we're going to put some of these things now to the test. This is the worksheet that I just emailed out this morning for those of you on Zoom. And it's asking you to do a whole lot of stuff, just drawing in different things and sort of interpreting what you see. There's a front and back to this worksheet, and I made the axes a little bit big on here just so it's easier to draw and extract information off of. In this case, since we've already talked about how to rescale the axes, in this case, I've put the tick marks on there for both the unprimed and the primed frame. I'm assuming we know how to do that stuff now, but it's good practice. You'll get more practice with that in the homework. In this case, we're concerned with drawing world sheets of objects and concerning ourselves with what the object is at a particular time. Since this worksheet's a little bit longer, I'm going to put the Zoom folks in a breakout room so that you guys can discuss it as you're working through it. And I'll come pop in and check if you have questions in a little bit. Notice you've got a straight edge on here if you want to draw really careful lines, right? That's why our protractor is not just a protractor, but also a ruler. So you can use the ruler part of it. You can use the protractor if you need to. If somebody asked us how fast CT prime, or the primed frame is moving with respect to the unprimed frame, we could figure it out by measuring the angle and then taking the tangent of that angle in our calculator, and the output would be V over C for that frame relative to the other one. Suppose I better redraw my axes while you guys are working. Notice that some of the answers aren't precisely defined. I didn't tell you where the stone is or whatever the thing was in part A. So there are lots of possible correct answers and lots of incorrect answers as well. Any questions in here? Reed, have you done the backside stuff? Or are you still thinking about the front? Okay. So remember, if something's at rest in F prime, its edges have to be parallel to the CT prime axis. That's just the same way as it would be in the normal, F axes. If it's at rest, its edges move parallel to the time axis. That's true for the primed frame too. Whoa, that was almost disastrous. All right, it looks like everyone's back in the main room now. So I just want to quickly go through the stuff on the first side because it's similar to some stuff that we've done before. Maybe the second side or page of the worksheet is a little bit more befuddling. And I should say I've changed the orientation of the camera because there was just a lot of glare from the window. So even though you're looking at a weird angle here, I'm hoping that at least it's not as washed out, but you can tell me if it's worse in some way. All right, so let's just go through them quickly. I'll try to draw them up here. I did the best I could in imitating the axes that seem like they were drawn in the figure that you're given. Draw and label the world line of a stone held at rest in F. Well, it didn't tell me. So F is the unprimed axes, right? So those are the horizontal and vertical ones. If I want to draw a stone held at rest, they didn't tell me where it's held at rest, so I can choose any location. But if it's at rest, it should be moving. In other words, it should be parallel to the CT axis. So that would be, you're supposed to label these. So I might put an A next to it, right? Or was that 1? That's 1. So I should put a little 1 next to it. That's my answer for 1. All right, please stop me, or if you're on Zoom, just unmute and ask a question if you have it. Draw and label the whirl line of a stone held at rest in F prime. Those are the primed axes that we have here. At rest always means its world line, or the edges of its world sheet, would be parallel to the CT prime axis in this case, if it's at rest in F prime. So it would look something like this line I'm drawing here. I'm drawing a line parallel to CT prime. That stone is certainly not at rest in F, but it is at rest in F prime because its X prime coordinate wouldn't change as time goes on. 3, draw the world sheet of a 1 light second long rod held at rest on the x-axis in F. This is like what we did on the previous one. I might hold it at rest between x equals 1 and x equals 2. My diagram, by the way, is going to get pretty messy, but do the best we can. Here are the 2 edges of the world sheet. And the world sheet I'm talking about is something like this. That's a 1 light second long sheet that's at rest, or sorry, a rod, 1 light second long rod, being held at rest in F. So that's my answer to, I guess we could say, I don't know where to label it here, 3. 4, how long is the rod in F prime? Well, we know its length in F, it's 1 light second long, but in F prime, I need to measure how long something that looks like this is. In other words, we slice through that world sheet parallel to the X prime axis and measure it using the scale on the X prime axis. And, I didn't quite line up with one on here, but it looks like it's quite a bit less than 1 light second, maybe 0.7 light seconds or something like that. Let's see what I got in here. When I measured on my paper, I actually got 0.83 light seconds, but I was doing a more careful job on the paper. You might say, does that look like 0.8 of a unit on this scale? Maybe, I don't know. So the answer to 4 would be approximately 0.8 light seconds. You might be able to get one more significant digit than that. 5, draw the world sheet of a 1 light second long rod held at rest on the X prime axis in F prime. So I need something that is exactly 1 light second long. And one way to do that is just to say, well, on this axis, the world sheet we're going to draw should go exactly between the 1 mark and the 2 mark. So let me just darken in that region there between the 1 mark and the 2 mark, and then I'll try to draw my world sheet in. That's a slice through the world sheet that I'm about to draw. And now the edges should be parallel to the CT prime axis if it's at rest in F prime. So here's one edge of the world sheet. Where's the other edge of my rod? It's at 2, right? One is at 1 and one is at 2. So it's going to be, and now I'm trying to draw a line that's parallel to the CT prime axis. It's kind of hard to see it. I'm standing so close on the board, but that's at least somewhat like it. Maybe I didn't get the angles exactly right, but we're talking about this is the world sheet right here. So that's the answer to 5. Yeah. It's 1 light second long in its rest frame, which is f prime. 6, how long is the rod in F? What do I do to figure out that last one, 6? How should I construct it on here, supposing I didn't know the length contraction? How would I just figure it out from the geometry we've been doing? Sure, it's at rest in F prime, and it's 1 light second long there. It's got to be shorter in F because it's moving in F. It's at rest in F prime. So what do I do? What construction do I do on here? What do I draw first? Or what do I look at on there? To the bottom, what am I looking at the bottom in particular? The x-axis, yes. So I look at the world sheet, and here is an instant in time in F, right? The x-axis is 1 instant in time in F. So this is a picture of what the rod looks like at an instant in time in F. And how long is it? Well, I need to assess this distance here. And again, without going to too much trouble, if I move over the left edge, trying to hold my fingers in the same place till I hit the 1 mark, it looks like it's about 0.8 meters, which makes sense, right? These two things are moving. A meter stick held at rest in F should be shorter in F prime, and a meter stick held at rest in F prime should be shorter in F, the same amount, right? And that's what we're seeing there, roughly speaking. I mean, I didn't make too careful of a diagram. Jesse? Well, there are lots of different places I could have put it. I could have put it here or over here. I didn't say where the stone was being held. So in the axes that are shown for F prime, everywhere on the CT prime axis is at x equals 0. This stone happens to be being held at a negative x coordinate, and it's staying at that same negative x coordinate as I hold it still. So that's a perfectly good answer, but there are lots of good answers that are positive. There's nothing shameful about the negative x coordinates there. Give them their due. They've got such a short bit of the axis, we should give them a little bit of the action here. Okay, any more questions on that before we go to the backside? This is kind of new stuff that maybe we haven't thought about as much, but we've got all the tools to do these kinds of things. Again, we're going to try to draw our answers in here, and oh gosh, I've really made a mess of my diagram here, huh? I need a fresh set of axes. Can I really erase just enough of the stuff so that I can not have to redraw this whole diagram? We'll see if I mess it up somehow. There's my CT prime. There's my X prime. So we need to erase this stuff. I usually draw, it's conventional when you're drawing these axes to draw a dashed line where a light pulse leaving the origin would be, just for reference. And then your CT prime and your X prime axes should be symmetrically on either side of that dashed line. And that dashed line should be at 45 degrees. I just kind of eyeballed it here, so it's not clear it's correct. All right, lots of mess on there, but I don't want to redraw it from scratch, so let's see if we can get away with it. A 1 light second long rod suddenly appears and disappears. So that means it just flashes into existence and it flashes out of existence as seen in F. And it's on the x-axis, okay? At some instant in time. We're not told the time. It could be at any time in this diagram. But it's 1 light second long. It appears for an instant, and then it disappears. So here, I'm going to draw a little line here that's 1 light second long, as seen in F. I think that's what we're told, right? It's exactly 1 light second long as seen in the unprimed axes. And as time goes on, there was nothing, there was nothing, there was nothing. There was a stick, and then there's nothing, 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 nothing. So this is a stick. Instead of having a world sheet, that's something that persists through time. If it's just a little snapshot, then that means it's only a thin sliver of time that it's there for. So that would be my answer to 1. Of course, I just sort of arbitrarily picked this point. You could have done something over here. Could have even done it in the negative x region. 2, describe in words what f prime sees in the case of 1. This is kind of interesting. So if this is what f sees, what would f prime see? See something moving? And so Jack just made a motion with his hands where he sort of went like this, but tell me in more detail, what would they see? Yeah, let's just say a nanosecond, some super short amount of time. Right, I mean, so he's exactly right. He said a shorter piece of the stick moving in the negative x direction, moving to the left in the diagram. How would we think about that? Well, we know every instant in time corresponds to a slice through. See, if we had a world sheet, we would slice through the world sheet with a line parallel to the x prime axis, and that would be an instant in time for f. So here's my x prime axis right here. I'm gonna, so here's a really early time. Nothing's appeared yet there, right? So they see, f prime doesn't see anything yet. Right at this instant, I'm trying to draw lines that are parallel to x prime. Right at this instant, the right end of the stick appears. So there's something that is right on this bit of, this is the x prime axis right there. There's something that's at one point, or a very small segment of a stick is sitting right there. So they just see just a tiny little point of the meter stick, right? At a slightly later time, I'm not doing a good job drawing parallel lines here, am I? I need to stand right in front of this to draw lines that are parallel to the x prime axis. Otherwise, I distort them. Here's a slightly later time. I'm trying to draw lines that are parallel to the x prime axis. At a later time, they find that this point has moved, right? It's moved to a different point on the x prime axis. And it's actually moved to the left, right? As I'm going off in this direction here, I'm hitting points that are more and more smaller x prime coordinates. So here's a bigger x prime coordinate, smaller x prime coordinate. At this particular time, and again, I'm doing my best to draw lines that are parallel here without measuring it all, maybe just the last bit appears there. So on the x prime axis, they see this little line of points go zip, right? So in this particular view, in x prime, they would see something, little bit of the meter stick moving over in that direction. They would see successively from 100 centimeters down to 0 centimeters appear, those little markings on the meter stick. What happens at an instant in one frame happens over a period of time in another frame. That's the relativity of simultaneity. So that's what we're seeing here. Here were a bunch of events that formed a meter stick in f prime. Those events are spread out over time in a different frame. Interesting. Well, we don't get to see this a lot because things don't just appear and disappear very often. And we don't travel that fast. 3. A 1 light second rod suddenly appears and disappears on the x prime axis in f prime. Draw the set of events comprising this. Have I lost almost my tick marks on here? Maybe, but here's the x prime axis right here. 1 light second so this is on the x prime axis at a certain instant in time. I'm just going to darken in or lighten in the region between the 1 light second and the 2 light second marks right there. So I'm just looking at this part. That is a meter stick that appears only for an instant in f prime. And now I bet the next question is, what would f see? Well, probably a similar kind of thing, except which direction is it going? This one's a little bit easier to interpret. Here's an instant in time for F. Here's another instant in time. Nothing's appeared yet. At this time, there's a point sort of to the left on the x-axis, right? Well, we can't see the whole meter stick. There's nothing over here yet. That point moves to the right and moves to the right, moves to the right, moves to the right, and then it disappears. So they're going to see the whole meter stick appear successively in little bits moving to the right. Just like in the other frame, they saw it successively appear in little bits going to the left because one is moving to the left and the other one's moving to the right relative to each other. Questions on that? Excuse me. What does the world line of a 1 second tick of a clock at rest in F look like? 1 second tick of a clock at rest in F look like? F is the unprimed axis. So a 1 second tick, if we imagine the clock sort of appears for one tick that lasts 1 second, if t, the amount of time here is 1 second, then c times t would be 1 light second. So it takes up 1 light second. It doesn't look very dark on there, but it would be something in between the 2 and the 3. Yep. How long does the clock tick last in F prime? Anybody tell me? Looking at this, does everybody agree that this is a 1 second tick? If it's a 1 second tick, that would be the change in t. The change in ct would be 1 light second if the change in t is 1 second. So I've darkened in this region. How would I draw a construction to see how long this takes as seen by F prime? Well, I need to sort of, draw lines of constant time in the F prime frame and see where they hit the CT prime axis. So I could, for example, where is a line of constant time? A line of constant time is one parallel to the X prime axis, a line of constant time in F prime. So that means I could, as best I could, go up here, try to stay parallel to the X prime axis. It's kind of hard for me when I'm so close to it to eyeball it. But here's a line of constant time. That's what we were talking about in that last thing where I was projecting those. This isn't going to work out so well for me, but I'm sort of off my axes here. Maybe we can do one between 1 and 2. How about that? Let's do a line of constant time. Should be parallel to the X prime axis. Draw it till it hits the CT prime axis. And what I need to measure is the duration of this as assessed in the tick marks on here. Now, my diagram's getting a little bit sloppy, but I'm expecting that it's going to be longer than 1 light second, right? A tick that if something is ticking once every second in the frame where it's at rest, as viewed from a frame when it's moving, those ticks will take longer than a second as assessed in that frame. I sort of eyeballed a lot of stuff on here, and I said this is like a 1 second time interval on, corresponding to 1 second for the CT prime axis. If I look at it, it looks like it's almost the same as 1 light second, but it should actually be something a little bit longer than that if you drew a careful diagram. On here, on my version of the solutions, I measured it with, drew careful angle lines using my, ruler and measured the distance and then converted by, 1 second is so many centimeters, and I got 1.15 seconds is the duration of that tick as measured in the other frame. I did a more careful job of it. What does the world line of a 1 second tick of a clock at rest in F prime look like? Well, I guess that's pretty easy. Here's one second clock tick. would be something that is a clock is at rest in CT prime, is sitting, it's going parallel to the CT prime axis, and maybe there's a light that turns on for 1 second and then it turns off after that, little LED or something like that. It would mark off that kind of space on the CT prime axis. And 1 second duration means CT is 1 light second. All right, I feel like that was a lot. It felt like a lot of work for me anyways, but we're just trying to get used to the mechanics. I mean, a lot of you said that the reading in Merman was a little bit confusing and there were an awful lot of diagrams. In some cases, the diagrams are easy to interpret, but a lot of the things he says with words, you really have to work hard looking back and forth with the diagrams, and sometimes it's easier to be in class and see them one at a time laid out like this, so I'm hoping that helps. We still have plenty of stuff to talk about tomorrow in chapter 17. We're not going to do everything that Merman talks about, but we will talk a little bit about the twin paradox. We'll talk about the pole vaulter barn paradox, which is the same as the garage paradox we talked about. I don't remember what Merman calls it. He also derives the Lorentz transformations from the construction we made here. We're not going to do that. It's just too much work. I think he derives the formula for the offset of clocks from this construction. We're not going to do that either. You read about it, but some of it's just too much to digest in one chapter. It's all in here. So the entire structure, if you've included the Lorentz transformations, you've included everything. So all those formulae are included in there because it matches the Lorentz transformations. And then we'll be off to different stuff next week, but not before we do another round of our presentations on Monday. So if you have questions on either homework or your presentations, if you want to talk about that, there were a few groups. I think I wanted to talk, maybe Spencer, if you want to talk about your stuff, and I think Jack, I was going to talk to you a little bit more if you have a second. And I know, is Muchiri on here? No, he's not, but I wanted to talk to him about his presentation as well. But anybody else is welcome to stay on. But if you're not staying, make sure I have your homework, and I'll see you at 12:45. And then again at 2:30, right? Thumbs up from Professor Kadavid. 2:30 is when we have our speaker today. Is that right?
That's correct.
We're having some movie presentations at 12:45, right?
Yes, and the groups presenting at 12:45, I will have the classroom open around 12:15 at the latest, but I'll try to have it open a little bit earlier than that in case they want to do some setup stuff.
Sounds great. So we'll see you on Zoom for that.
Yep, see you soon.
If you want to keep these protractors, I'm not sure, just because I haven't just looked at the homework for chapter 17. You may need one for some of the problems. So if you don't have a protractor somewhere, Jack suggested a method that you could get around it, right? You could just say, if V over C is 0.7, if you go up 1 unit on the vertical CT axis, then you go over 0.7 units, and that would give you, and then you connect those points, you get a line at the correct angle. So you don't really technically need the protractor. But if you want to keep it, just make sure you remember to give it back to me, because those belong in the physics lab. See you in a bit. Looking forward to those movie presentations. Okay, so you have homework questions, Reed? Okay. Okay, let me see if I can quickly just talk to these guys. So Spencer, I was talking about the opposite thing happening, as I thought you said in your talk, right? That it would explode.
Yeah, I think it shouldn't, just off of how the premise is set, because if the proper length of each of these, it just barely doesn't touch, then the length contraction wouldn't make this case, because this one's lagging, and so this event happens before this event, where like these, I'll be able to express it, and I'll try to get these images in a way that I can have multiple clocks to.
Yeah, and I mean, you're welcome to just, if they're not clear enough in the PDF, when you crop them out of there, I'm happy to give you the original Word document that has those pasted in there too. Yeah, they're pretty simple. So then how are you going to answer the question of, this thing's going in this direction, and what happens as time goes on? As we're watching this film from the frame where it looks like this thing's at rest and this thing's moving, its length contracted. What happens when this looks like it's going to hit that? What's your explanation for what happens at that point?
It's weird, but we were talking about the rigidity and how nothing can be perfectly rigid. So that's where I was wondering about the collision. Could it, stretch or compress it at all? But I don't know if that was what I was asking. And
well, if there is a collision, it seems like the things that are going to collide are this and this, right?
But this happens, so it's like measuring the fish. And so this happens before this. So we hit these two edges before the detonator hits the explosive.
Well, so that is going to be, so these are clocks that are, if they're not reading the same thing, there's clocks that are attached to this thing as it's moving, right? And when the clocks are moving, if they're synchronized, they're not synchronized in the frame in which they're moving. So these could help us figure out the order of events as seen in the frame where this thing is at rest. But we already kind of know the order of events in there. From this point, it seems like these little stopping bars are going to hit those first, right? And this thing won't even be close to there. And that's the paradox statement, right? I mean, either it gets stopped and we assume it's hard enough to keep it from going any further, and then, I guess once it's stopped, it turns into its normal length, but it's just short of being able to push that thing. Or if we look from this point of view, it seems like these two things are the first thing to touch. And if they are the first things to touch, maybe the order of events is different, but if the order of events is different, it seems like two different things happen, and two different things can't happen because it either blew up or it didn't.
Yeah. Am I wrong to understand it? And I realize this might not, I don't know if you could have this in reality, but like...
Probably not, technologically speaking.
Yeah, this bottom T part would so if this happens beforehand, this extends a little bit. Oh, now I'm getting all switched up, but it almost these two hit and then this keeps on going a little bit to catch up with this.
Yeah, it does keep on going because, you can think of where's the first part on this T to get the message that it's been stopped. This is the first part that gets the message. Now, this hasn't gotten the message yet, and there has to be some sort of signal. It comes through the, successive molecular forces. Some little wave propagates through there, and that can only propagate so fast. And the fastest it can propagate is the speed of light. We can imagine, okay, in an idealized case, maybe it's going to be no worse than the speed of light, or no better, depending on your perspective. Now, during that time when that message is propagating forward, these two things have slammed in there. We imagine this thing is as rigid as it could possibly be made. Still, the front is going forward after those have slammed into there. And the question is, does the signal get to the front fast enough to stop it? Or is it already a foregone conclusion that this is going to hit there before the signal is able to propagate from the arms of the T up to the front with the detonator? Now, I think it's pretty clear from this one. When I look at this case, it's like there's no way, if you watch a movie of this short little U is just going to progress forward, forward, forward. And the first thing is going to hit is the detonator on the explosive, right? So I know when I look at that middle picture that the explosion is going to happen. And the only question is, how could it still happen given that this short little T slams into there? And we imagine that's not destroyed by that process, but it's very, very hard stuff. And somehow you stop the arms of the T. Well, just because I yank on one end of a moving meter stick and stop it, that doesn't mean that instantaneously there can be the other end gets the message, because signals about what happened, that one part of it is stopped, can only travel at most the speed of light to other parts of it. And when we're talking about mechanical waves, they're generally much less than the speed of light. But let's take the most worst case scenario or best case scenario that it propagates at the speed of light.
Okay, I get that now. I was just assuming, I suppose naively, that the proper lengths together in the same IRF, like there'd be no way physically that it could touch the
synchronized in the ship's crew, because they measure, like it goes by 1 year, so they each measure a year, like simultaneously.
Well, I don't know what you mean by simultaneously, because after that first year is over and ship 1 launches ship 2 ahead, we're not really going to pay attention to ship 1 anymore. Then we're concerned with ship 2. We're riding along with a crew member in ship 2, and they assess 1 year is going on their watches. What does the Earth assess as that time? But they're going faster now with respect to the Earth than ship 1 was. So we don't need to worry about the crew on ship 1 after that first calculation.
Okay.
And then what is C for a crew member who rides? Oh, okay. So if someone keeps getting on the ships, they get blasted ahead, and then they get on the ship before that one's blasted ahead, they would experience 7 years if they go through the 7th iteration of this. How long would that process take on Earth? Well, you just add up the first 7 times of the series that you're getting in B.
Yeah.
And on your calculator, you probably have to just type everything in from scratch on that calculator. On these TI calculators, there's ways to just sort of hit enter, 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 and it gives you all the answers without typing more stuff in.
Yeah.
And that's what I was trying to indicate in B or A, I guess.
Yeah. So it's for the first one on B, it's 1 times gamma,
Yes.
because then it would be big.
So it's 1.40 years is what you should get. And then the second one, you should get 2.92 years, according to me.
Yeah.
You know, also on the TI calculator, I don't know if you can do this on yours, but you can bring up the previous thing you typed in and just edit that one number and hit enter again, and then it, without typing the whole, you know, square root and the square and all that stuff in.
Yeah, I can do that.
Or the other possibility is always Excel, where you drag the formula down if you ever do that kind of stuff. I know we might have done that once or twice in Physics 110.